And if you are having issues uploading photos, submit what you can. As long as I see a submission, I will count you as participating. Whatever you can do, I understand that this is not ideal. It's, yeah, a different kind of challenge. But just to go through some of these questions, the first one, this is kind of a fancy version of what I was looking for in that first model that I asked you to draw, where we can see the moon kind of rotating around the Earth. And based on where it is with respect to the sun, we see different phases. So if the moon is between the Earth and the sun, we see the dark side of the moon, the unilluminated side, and we see a new moon. If the moon is on the opposite side of the sun from the Earth, we see the entire half that is illuminated. So we see a full moon. And then kind of going through, we move through the waxing and waning phases, the crescent and the gibbous, and just, yeah, the illuminated half always points towards the sun, dark half always points away. Depending on where it is with respect to Earth, we see different amounts of the illuminated side.
Wait, I have a question about that real quick.
Yeah.
When we were drawing the third quarter and the first quarter, you know how it shows the third quarter and then the little moon right above it, they're opposite because of which one's facing the sun versus how we see it. When we're sketching that, do you want us to draw it like how we see it or how the sun is pointed at it?
For this activity, just how the sun is pointing at it is fine.
Okay.
Yeah, this is just a little bit more of a fancy version. I don't need your models to be works of art ever. Any other questions? Right now, I was running this morning, and when I got up, you could see the full moon pretty much, and it was beautiful with the pink clouds. So if you do go out and see the moon now, it's pretty close to full. Okay. The other questions that were kind of towards the end, I talked about the timing of the different phases of the moon. And so the idea of how we figure this out is you can kind of place yourself on your Earth model, and based on how the where you are with respect to the moon, you can figure out what time it is, or with respect to the sun, sorry. So if the sun is directly overhead, it's noon. If you're on the opposite side, it's midnight. And then we have sunset and sunrise on the two opposite sides. So 6 a.m., 6 p.m.-ish. So if the full moon is directly overhead, we know it has to be midnight because the sun has to be on the other side of the Earth. That's why we're seeing the fully illuminated moon. The new moon is always going to be overhead exactly at noon. You can't really see it anyways. You can't see it during the day, but also there's nothing really to see. So the new moon would be overhead exactly at noon, and we can kind of figure out like the third quarter, or the first quarter, sorry, would be right overhead at sunrise. Third quarter would be right overhead at sunset. And we can also think about, yeah, when you see the full moon rising right at sunset, and we see the full moon setting right at sunrise. So this is kind of what I'm trying to get at. If you can add these things to your models, if I ask questions about this later in class, this is kind of the idea of how you can figure out those timing questions. This is a little funky. Does anyone have any questions about that? So the other thing that the moon rotating around the Earth causes, besides the phases, is the tides. So we get tides on Earth because of the gravitational pull of the moon. So this is the Bay of Fundy in Canada, between Maine and Canada, I think. It experiences some pretty extreme tides, more than other places on Earth. So you really have to pay attention to where the moon is if you want to take your boat out and you don't get stuck. Other places might not have as extreme tides, but the idea is that this is just because the difference of the gravitational pull as the moon moves around, or as the Earth rotates, and the moon ends up being directly above different places. So if the moon is directly above you, you are experiencing a high tide because the moon is pulling up more on the upper levels of the Earth, more on the side of the Earth that's closest to it. And then on the exact opposite side, the Earth is being pulled away slightly from the ocean. So we're getting a high tide exactly on the opposite side of the Earth too. And then low tides directly at your kind of opposite point, the points perpendicular from where the moon is. So if you're in line with the moon, if the moon is either right above you or through the Earth from you, you are experiencing a high tide. If the moon is kind of rising or setting from your position, you are experiencing a low tide. The other thing, obviously, in our system is the sun. So the sun also gravitationally pulls on the Earth. And because so our gravitational equation, it was over r squared, that distance is really, really important. So if you're closer to the object being pulled on you, it really affects you. So having the moon and the sun on the same tide causes a larger tide than when the Earth and the moon and the sun are not directly aligned. So there's our spring tides is when everything is nicely lined up and you have a slightly higher high tide. And then neap tides are when everything is lined up and you have a slightly lower low tide. So it's just the gravitational pull from the moon, the differentiated gravitational pull from the moon causes tides. When we get to black holes, we'll see how this also what would kill you if you went through a black hole. You would get torn apart by the differentiated gravitational pull from a black hole. So it's just showing this again. So what's happening is as the Earth rotates, you're getting pulled differently based on where you are. So the tides are getting kind of pulled out by the moon as the Earth rotates through one day. So that's why we have 2 tides in a day, one when the moon is directly overhead, one when the moon is directly beneath your feet. So 2 high tides, 2 low tides. Any questions about tides? The other thing that's kind of crazy is that the tides don't quite happen perfectly, and this is, and they cause something called tidal locking. So the angular momentum of our system is not quite perfectly aligned because of friction. The tides aren't going to happen exactly when the moon is right overhead, so we get kind of a mismatch between where the gravitational pull of the moon and where the tides are. So it's not quite perfectly when the moon is overhead, and that actually slows down our Earth-Moon orbit system. And it's caused, at this point, the moon has slowed down, so it rotates, it spins around one time every time it makes one orbit around the Earth. And so when we say the dark side of the moon, a lot of times what this means is it's the side of the moon, not the side of the moon that's unilluminated, but the side of the moon we never see from Earth. So there is one side of the moon we never see from Earth. So on this image, this little stick is it's like we put a flag up one part of the moon, and as it rotates around, that flag is always pointed towards Earth, because one orbital period and one rotational period on the moon are the same, because it is tidally locked. So it has been slowed down by the force from the tides, slowly slowing it down over time. The same thing is actually happening on Earth. So the differentiated pull from the tides is actually very slowly slowing the orbit of the Earth, or the rotation of the Earth. So days are getting very slightly longer because of the moon at a rate of about 1.5 milliseconds per century. And the moon is getting slightly further and further away from us at a rate of about 3.8 centimeters per year. So because of these differentiated tidal forces, the moon is slowly moving away from us, and the Earth is slowly slowing down. So 100 years from now, a day will be 1.5 milliseconds longer than a day is today. Which is kind of weird. It also is weird to think about when the dinosaurs were alive, the moon would have been larger in the sky because it was closer. So not much has changed in terms of like human lifetimes, but the dinosaurs did see a bigger moon than we see because the moon was closer to them, to Earth, when dinosaurs existed. Any questions there? So the next thing I want to do is we're going to talk quickly about adding eclipses into our models. So an eclipse happens when we get everything in nice alignment, and either the Earth, we have a lunar eclipse when the Earth blocks the light from the sun. So normally we would see a full moon, but the moon happens to be in the Earth's shadow. It's not getting any light from the sun, so no part of it is illuminated, and we see a lunar eclipse. Of course, there's still some scattering of light through Earth's atmosphere, so the moon ends up looking kind of red because the red light gets scattered through Earth's atmosphere and we see a full red moon, but we call the lunar eclipse because the Earth is between the sun and the moon and the light gets blocked. So we have everything nicely aligned and we see this reddish moon during the eclipse, when the moon is in the Earth's shadow. The other thing I thought was kind of fun, I learned about this recently, Aglionis was kind of the first female astronomer. She and her work, what she would do is she would predict when eclipses happen. She was around during ancient Greece-ish times, and she was also a member of something called the Witches of Thessaly, which I thought sounded cool. So female astronomers back, if I was an astronomer in ancient Greece, I could be a witch. But I'm in Walla Walla in the 21st century, so probably not a witch, unfortunately. Other kind of eclipse, there's lunar eclipses, and then there's also solar eclipses. They're kind of the opposite. A solar eclipse is when the moon is directly between the sun and the Earth, and the Earth is able to, and the moon's shadow ends up on the surface of the Earth. So the moon casts a shadow when it blocks the sunlight, and if that shadow hits the Earth, we see a solar eclipse. And just to kind of show this, this is a video made for the 2017 eclipse. What we can see is the moon shadow, which is smaller than the Earth's shadow because the moon is smaller. If it is able to hit the Earth, then we can get a small path where we will see a lunar eclipse or a solar eclipse. Solar eclipse is when the sun gets blocked. Lunar eclipse is when the moon gets blocked. Okay. And this is the path of the 2017. So the moon shadow is landing on the Earth, and the sunlight is blocked, so we see a solar eclipse. And what's pretty incredible is that for solar eclipses to happen, we need the moon and the sun to be approximately the same angular size. So we need the moon to be big enough that it can block the whole sun and close enough to us that it can block the whole sun. And so on Earth, nicely, both the moon and the sun are about half a degree on the sky. And so we actually are able to see full solar eclipses. If that was not true, if the moon was further away, we might not ever see a solar eclipse. If we were closer to the sun, we might not ever see a full solar eclipse. But everything is nicely aligned for us at this moment in time that we can see solar eclipses. But the idea is that they are fairly rare because we do need that nice alignment between the Earth, the moon, and the sun. We need the moon to be at a point in its orbit where it's closer to Earth, so that shadow can actually land on the surface of the Earth. So we need the moon to be near at perigee, so at its closest point to Earth. There's perihelion when you are closest to the sun. Perigee is if you're closest to Earth, when the moon is closest to Earth. So we need that to be true, and you need to be on a position on Earth that the shadow actually hits. So that's why in 2017, when the solar eclipse came through, there was only this kind of small little area where the full solar totality could be observed. So luckily, I think Walla Walla is like right around here, so it wasn't quite in totality, but it was close. For me, Laramie is like right here-ish, so I was able to see it in totality. Was anyone else gonna see like hands? Were people able to see the solar eclipse? Like shout out.
No, I remember looking at it, but I remember like when it happened, but I know I wasn't in full totality. Like I just remember it like that's a big eclipse. Have all the little eclipses.
Yeah. And Ellie,
I, w- I was in Portland and I got to see it in
I,
totality. Yeah.
what was it like?
Well, I was at work, but there was nobody in the streets. Everyone was partying because it was a solar eclipse. And like we literally popped champagne at work and we're like, it's the eclipse. But it was pretty crazy, honestly.
Yeah. Anyone else have fun eclipse experience?
I was in Illinois and I went camping with my sister. I was a senior and I skipped my class and we went camping. So like we stayed there the night before and then woke up, took a hike and like had our glasses to see it.
I was out. We were my advisor and I went to a lake and we did some like outreach stuff with folks at that lake to help them see the eclipse through a telescope and with a solar filter. Um, but it was fun when it went down. All the crickets started chirping because they thought it was. We could like hear the crickets get super excited, which was just really cool. Like hearing all the people around, like ah, it was fun. It was fun to be a part of. Like Allie was somewhere where it was cloudy. It sucks. Yeah, we were. I think that was like everyone's fear. Like once it happens, you can't drive anywhere. You're stuck. But yeah, it's like the most. I think the population of Wyoming like tripled or something during that period because everyone was coming to see it, and usually there's no one in Wyoming. But it's fun. Okay, so we've got about 10 minutes left, and I want 5 of those to talk about some homework stuff and scheduling changes. So what I might do is really quickly run through the homework stuff and then put you back in your groups. And if you want to get through as much of the eclipse thing as you can, that's great. And then we'll start next class by just kind of reviewing the answers to that. If you need to go, don't worry about it. If you did your model, I'll count that as participation credit for today. So the first thing I wanted to point out is that next week on the 8th and the 9th, there's going to be something happening called the Scholar Strike, where this might be something that you've heard about in other classes, but there's just a move to kind of try to stop normal business as normal in academia, to recognize what's been going on with racial violence, police violence towards Black identifying people of color specifically. So similar to what the WNBA and the NBA and some of the other sports leagues has done, there's a move to have academics try to strike in some version. So my idea, what I want to do for this is that next class on Tuesday, you'll see I've kind of moved a few things around. So instead of finishing this discussion, I want to have a conversation with anyone who would like to join about decolonizing STEM and the situation at Mauna Kea with the 30-meter telescope. So I've added some articles about the different things happening there. I have very mixed feelings about this, so I would love to have a conversation with anyone who is willing. This will get you 2 participation points, but there will be extra points, so you can get your total participation grade without attending this day. You don't have to. This will be kind of like extra credit. So I want you guys to take the time on the 8th and 9th to do what you need to do. If you want to join in, I will be here and I would love to have these conversations. You don't need to do any of that reading, but these are also great articles if you are looking for something for a science podcast or article project. These might be interesting ones to check out. Again, kind of focused on the situation on Mauna Kea with the 30-meter telescope and how different groups have reacted to that. So I've moved a few things around. That means I have moved our solar system test one day later. So you have a little extra time to earn points towards that badge, but we are getting close to about halfway through our first badge. So you should be starting to think about where your points are. So if you haven't submitted a homework assignment yet, start thinking about that. We have one more reading quiz, but that'll get you up to 10 points. And then if you want to do one of those different types of projects, the biography project, the citizen science project, the podcast project, article project, or a just kind of open-ended, those things, should start thinking about trying one of those. We also have, let me pause this for a sec. Share our homework assignment. There's also the one homework assignment is up, and we have now gone through the information you need to do most of this. So this is your planetary science homework assignment. You can do as much or as little of it as you want, but we've already talked about sky coordinates, so you can answer these parts. We've talked about Kepler's law, so you should be able to do most of that. We've talked about gravity, so that should be stuff that you've seen before. We've talked about seasons. I think there's a little typo there, but sorry. But you should be able to do that. And now we've also started talking about the Earth-Moon system, so you might be able to get through some of those questions as well. So there's just a few on this that we haven't covered yet, but it might be a good idea this weekend to start thinking about getting through some of that homework, because we're about halfway through our first badge period. And on the same note, on the labs, we're about halfway through our lab badge earning period. So if you've done the math in astronomy and the planetarium lab, you should have about 12 points, which is half the points you can get. If you haven't done either of those, there are still other labs to do. You can still do those two labs. There are other labs you can do as well. I think the planetarium one is up now. The scale model solar system one is up now, which is also a lot of fun. That was, when I taught this class before, that was people's favorite lab, was making a scale model solar system. So those are some options for things you could be doing for lab. Next week, the last two planetary atmospheres, surfaces, and the measuring the composition of Saturn will go up. So there'll be a lot of options for labs starting next week too. I'm going to send out an email asking if people want to be put in lab groups today-ish. So if that's something, if you want to work with people but maybe don't want to come to the lab time, I can try to pair people together who want to work together, and then you can find a time either in the lab time or whenever works for y'all. I'm just probably working virtually together, so similar to our breakout rooms. Does anyone have questions about all of that?
How do we track our points?
So I've been doing my best in our lab, in your grade book on Canvas, to update things fairly quickly. So
Yeah, I have the syllabus thing and I know the thing, but you just said 40 things and I'm like, shit, I thought I was doing stuff, but am I how many points do I actually have? And it's just do I only have 30 points when I need 70 to 100? You know what I mean?
Yeah, so the other thing I'll write an email trying to hit on this a little bit more. But before the test, there are 70 points kind of pre-test, and then the test is 30 points as well. So,
okay.
Yeah, so don't freak out if you're not as close as you thought. The idea is right now, you should be getting close to 35. So if you look in your grade book, if you add them up and you're getting close to 35, that's awesome.
Yes.
But if you aren't quite there, you might want to start thinking about either going back to the reading quizzes, working on some of the homework assignments, or going through the labs. My lab grading is mostly happening on the weekend, so I try to do those as fast as I can, but usually if you submit a lab, it'll be graded the following weekend. Any other questions?